In this session, we'll discuss about the Bode plot. This was formulated by the Bode, and it is basically used to draw the response between the input and output. It is drawn between two responses. One is frequency versus the magnitude, and other one is frequency versus the phase. Let's take a small example here. In this example, I'm trying to draw a particular plot with reference to the frequency on x-axis and amplitude or the gain on the y-axis. For any plot, there are, it may be one or two frequencies are there. In this particular figure, there are two frequencies are there. Those frequencies are called cutoff frequencies or corner frequencies. So what is the purpose of it? As you know, when you have seen, when the magnitude is reaching to 3 dB, either it is going in the, from that 3 dB can say that whether it is going in the amplification zone or whether it is going the attenuation zone. From the previous example, when you observed, when the gain is 2, it is starting from the 3 dB. When the gain is 0.5, it is starting from the minus 3 dB. So we need to find out that particular either plus 3 dB or minus 3 dB point, which is very important in the frequency response analysis. So to do that, let us have one example for the lead network. So what is the lead network? In the sense, I am just trying to talk about only the voltage gain response here. In this lead network, I am trying to show you a particular AC signal I am giving. That AC signal I am passing it to a capacitor C, and I am taking the output across the R. When I am showing this lead network, that means that the output is, that means the output voltage is leading the input voltage. Here my input voltage is a sinusoidal signal, that is, and I want to take the output at the resistor R. You know, here one important thing that you can observe, the gain of this system is generally is output by input. When you are putting that gain in terms of decibels, you generally have written last time it is 10 into log of gain to the base 10, but those type of gain is applicable only when you are trying to draw the gain for the power. When you are trying to draw the gain for the voltage, it should be multiplied with 2, because the power is directly proportional to square of the voltage. So 2 will be multiplied, the gain will become 20 into log g to the base 10. So for this particular kind of RC circuit, the cutoff frequency can be written as per the standard equation, Fc is equal to 1 by 2 pi RC. Now let us take first of all, from the electric circuit analysis point of view, we'll try to see how can we write the output voltage to the input voltage ratio, or we wanted to find out what is the gain for it. So as per the potential divider arrangement, the total output voltage is equal to across the R is equal to input voltage into voltage drop across particular resistor R divided by total resistance R plus J XC. So you can write, R minus J XC. For the simplification, for our understanding purpose, I just write R plus J XC. But it is actually R minus J XC. So for this particular R, the gain V out by V in R by R plus J XC, the gain can be written as R by magnitude in terms of square root of R square by square root of R square plus XC square. So in this one, the two things that we need to understand, one is what is the cutoff frequency, that is Fc, or critical frequency, and the frequency that is written, that is denoted by letter Fc, and the frequency of our interest where we wanted to find, that is written as F, and the total decibel gain is written as AV dash. First, let us do one thing, and then let us write the actual modulus gain of this particular ratio, output by input. That is, gain can be written as square root of r square divided by square root of r square plus xc square. So as you know very well, this thing, very important thing, in the capacitor, as the frequency increases, the reactance of the capacitor reduces. As the frequency reduces, the reactance of the capacitor increases by the formula xc is equal to 1 by 2 pi fc. And from our earlier formula, the cutoff frequency, or you know that from there f is equal to 1 by 2 pi rc. From there I can write r is equal to 1 by 2 pi fc. So I wanted to find out what is the ratio of xc to r. I can simply say that it is fc by f. So let me substitute that value into the gain. Our gain is av is equal to r by square root of rc square plus xc square. Now when I divide that with r on numerator and denominator, I'll get 1 divided by square root of 1 plus xc square by rc square. So xc by r I know because I wanted to know what is my critical frequency. That's why I wanted to put xc by r as fcc by f. So if I put that is fc by f, the total gain will become 1 by square root of 1 plus square root of fcc square by f square. Now I wanted to write the decibel gain for it. The decibel gain for it is 20 log to the base 10 of the gain, that is 1 by square root of 1 plus fcc square by f square. That is most important point that is here. Now let us see how can we draw the, for this particular gain you can draw the Bode plot for it. So yeah, let's take into new page and we'll try to draw the Bode plot for it. So as I told, the Bode plot can be drawn for the phase between the frequency and the magnitude, between the frequency and the phase. Now let us only draw about the Bode plot between the frequency and the magnitude at the cutoff frequency. Say for example, when frequency is such high that the amplitude, the input amplitude is completely passing through the output amplitude. At the time, when the frequency is high, the capacitor reactance is negligible. Whatever the input voltage that you are giving, same will be impressed across the output voltage. At the time, the gain is 1, decibels of gain is 0. And when you are below that critical frequency, what is happening, the dB is getting reduced, that is minus 3 dB minus for every change from 1 to 0.5 or 0.25 or 0.125. This is the how the graph that will be coming for your lead network. So let us this is a kind of representation of the Bode plot using these two asymptotes. Asymptotes are those which are approximate, values are the curves that we are drawing it. Let us verify with the help of a small simulation using NI multisim. This is one of the good software that I have observed, where you can get all those values very nicely here. So first what you do, you can select the component from the power sources. You can take the voltage source, and we are using capacitor and resistor, so we'll take the next component as capacitor from the basic components. I'll choose the capacitor. You can choose any value depending upon that particular value. The corner frequency will be defined. So I'll take another value, that is resistor, because I wanted to know the output at the terminals of the resistor. So now I have taken the capacitor, resistor, and I wanted to connect all of them. So with the help of a wire block, I'll connect all of them, and then see, you can observe carefully. For the purpose of minimization, I want to show you in particular zoom. So I can connect the capacitor terminal to the resistor and the other resistor terminal to this one, and I wanted to my main area of interest to see the frequency response from the input to output. The input is V1. That of course you can have flexibility to change that value for any value whatever you want. And I wanted to plot the Bode plot, so I just brought the Bode plot tool from the extreme right side. So I'm just connecting the in plus and in minus to the input terminals, and out plus and out minus at the output terminals. because my area of interest to find out the output at the across terminals R1. So I have connected that, and as I told, we have a flexibility to change the input voltage. So just by double click on this one, you can change the voltage whatever the value you want to change, for example 10 or 20 or whatever the value that you wanted to change, and whatever the frequency that you wanted to change. It could be 1, it could be 10, or it could be 100. Any value you can change. Now you can start running the simulation by pressing the green button there. Once you start running, you can observe how the Bode plot is getting plotted here. So probably you are able to see it clearly. So here there are two plots that you can see. One is magnitude and other one is phase. So right now I'm trying to change about the magnitude. I wanted to see where is the minus 3 dB point, because from where it started bending, right? That is called one of the lower cutoff frequency or lower cutoff frequency. So this is one minus 3 dB point that is happening here. So that can be changed and tracked, and you can find that as the frequency increases, you can see as the frequency increases there is a 0 dB. 0 dB in the sense the complete input is just getting applied at the output. So the input is equal to output, and the effect of capacitive reactance is negligible. As the frequency reduces, the effect of capacitance is coming into picture, and the signal is getting attenuated. Attenuated in the sense the signal is whatever the input that you are giving, that output you are not actually getting, you are getting less than that particular output. So now till now we have seen how to draw the magnitude plot. In the same way, even let's draw the phase plot. So as I told you, the phase plot is what we wanted to draw between the frequency versus the phase. That means when you are sending a signal, so whether at lower frequencies what is happening, as the frequency increases what is happening, that you wanted to observe graphically. As I told, it is leading. So at lower frequencies it is leading, at higher frequencies the whatever the signal that you are giving, the same signal will be impressed across the output. So from our earlier formula, the output voltage by input voltage is equal to R by R minus JXC. For our convenience, again I am telling, I have written R plus JXC. However, it is R minus JXC is the actual value. So that is, for this one we have already written the magnitude, and for the phase we can write that minus r at an angle of 0 by square root of r square plus x square at an angle of minus tan inverse of xc by r. So if I take the tan inverse to the above, it will become positive. So finally theta is equal to tan inverse of xc by r. Now if I, as I mentioned, if I try to draw the plot between the frequency and the phase, you can see the same thing here. So when the frequency is lower, xc will be higher. When the xc is higher, in the sense it is at 90 degrees. As the frequency is further increased and increased and increased, xc will go on reduces. And when the xc go on reduces, the angle will become 0. So that's how the phase plot will start from 90 degrees, and then go on start bending. So now here also we need to observe at what particular phase angle this is getting changed. So that particular phase angle is called the critical angle. That is what in this case it is 45 degrees. So now let us observe from the simulation and from the multisim perspective, what is the 45-degree point, one, why it is having so much amount of significance. So this 45-degree point, it should be the 3 dB point. It indicates that where the it indicates that in what way the signal is moving, whether it is going in an amplification way or it is going in the attenuation way. Now let us see at the phase plot. Just besides the magnitude plot, there is a phase plot, and if you see it, so it is starting from 90 degrees at particular frequency. You can see at what frequency it is around about. So I wanted to see that where is the 3 dB 45 degrees is happening. So 45 degrees is particularly exactly happening approximately at 155 hertz. Same thing, let us see here 45 degrees, where at 155 hertz, what is the dB value. So at 155 hertz, if you see, it is approximately the minus 3 dB point. That is what the catch point is. That is why the 3 dB point is more critical in finding whether the whether the signal is attenuation or amplification, or what is actually happening, because that is where the critical frequency lies. It has two critical frequencies generally. If you combine the lead and lag network, the same thing will apply for the lag network.